Welcome to Study Loop.
In this problem, the fundamental equation that we will use to solve for every needed value is the equation of the ideal gas, which is given here. We have two states. We have two corresponding temperatures for two states, and this equation is very important because we will substitute for the temperature. We will derive the temperature from the ideal gas equation for every state that we are given. These are two states. And from these two equations, we will combine them and solve for the relationship between the initial and the final temperature, or the T and T0 temperature. So first, let's derive the temperature from the ideal gas equation. It will be just divide both sides with nr and obtain that T equals PV over nr. Therefore, for the T0, it will also be equal to P0, corresponding pressure and corresponding volume, and N and R are constants. So we can say that the ratio of T over T0 is going to be pressure times volume over nr over P0 V0 over nr. So these parts will cancel out, and we have only PV over P0 V0. Now we can also substitute directly here, but we will transform this once more. So instead of substitution, we will say that since we need to find the relationship between the two temperatures, we'll say that the T equals T0 times, and now we have P times V over P0 times V0, and then substitute. So this will be T0 times, and here we have 10 to the 5th power pascals only, times, this is going to be in meters cubed, and here we will have 3 times 10 to the 5th power pascals times 0.02 meters cubed. And when we place these values here of this division, of this fraction, into a calculator, we obtain that all these values actually computes to be equal to 1. This is equal to 1. So in that case, T equals T0 times 1, or simply T equals T0. And this is a very important relationship for this problem. And in the next step, we need to find the work done due to the change of volume under the constant pressure. So let's remind ourselves that the work done, this is from the law of force and generally the expression of work in relationship to force, but adjusted to thermodynamics problem. So W, or the work done, is equal to constant pressure times the change in the volume. So we can simply say that this is equal to V2 minus V1, V final minus V initial. And when the gas expands, it does the work on the surroundings. So it also causes the surroundings to move and expand. If the gas moves slowly and the pressure is constant inside the gas, then we can get the total work done by the gas under the constant pressure, like in this case. So here, the final answer for this part of the problem, this is the part A of the problem, is that T equals T0, and that the work done will be expressed by this formula right here. Now for this is the part A. Now for the part B of the problem, we need to actually evaluate the work done in the path from the point B to the point A, where there is a volume change. So the work done in that case from the previous formula we know equals P times V2 minus V1. And in this case we can simply substitute that the constant pressure is 10 to the 5th power pascals times 0.06 meters cubed minus 0.02 meters cubed. When we put these values into a calculator, we obtain that the work done is equal to 4,000 joules. And now for the part C of the problem, now the change in the volume is positive, so the work done also must be positive because the pressure changes with the volume. And we also know that the area under the curve is always equal to the work done by the gas. So for the part C, the area is a triangle and the rectangle together. This is observable from the problem given figure from the PV diagram. So we only need to take the coordinates, pressure and volume coordinates, and add them together. Add them at their corresponding surfaces below the lines. So for the part C, it will be the W equals, first for the triangular part, it will be 1/2 of the 0.06 minus 0.02 meters cubed. And then times 3 minus 1, this is for the pressure change, times 10 to the 5th power pascals. And now for the rectangular part of the area under the line on the PV diagram is, so this is going to be plus 0.06 minus 0.02 meters cubed, and simply times 10 to the 5th power pascals. When we put these values into a calculator and evaluate them, we obtain that the work done in this case is 8,000 joules. So always remember that the work done is the area under the curve or under a straight line or under a combination of two straight lines, like in this case where one is a triangle, another is a rectangle, but it's always the area under the line on the PV diagram, on the pressure volume diagram. So that is an important point. I hope you find this helpful, and I hope to see you in another lesson.